Hi, in this module on nature of materials as part of this course on basic construction materials, we will be talking about atomic structure and interatomic bonds in this particular lecture. So, this is the outline for this module. First we will talk about atomic structure and bonding, and then we will talk about metallic materials, where we will talk about lattice structure, grain structure, and then alloys, phase diagrams, etc. And then we will look at inorganic solids and organic solids. So, this will be about 4 lectures, and today we are going to look at basic material concept, which is atomic structure and bonding. That is what is included in this particular lecture, and these are the textbooks I have referred for this, and also as I mentioned a lot of schematics etc. from the internet have been used to demonstrate various principles. Okay. Now, before talking about atomic bonding and all that, I would like to bring your attention to something which is we are all familiar with, that is pencil. And have you thought why some people call it lead pencil? So, we will look at that. So, it was when this particular material was discovered in 1600s, the black lead, it was some sort of black color lead, it looked like that, and rather than a form of carbon, and hence the lead pencil, people started calling it lead pencil, although it is not really lead. Now, sticks of pure graphite is what is actually used in our pencil, and they are very brittle in nature, as you know it very well. When you push it hard onto the paper, and if it is a hard surface, it will break, as I had shown a picture on the bottom right side. And because of this brittleness of this graphite stick, where people put that in the wooden tubes, or so you drill a hole in the wooden, that is how the pencil is made, and then you keep this graphite stick inside and then compress it so that it does not come up very easily. And then here you have another example where a modern type of pencils, where you have steel or a metallic tube and a very thin stick is kept. And it is very important to have that tube all the way to the tip, so that you do not really break it. So, the lateral force coming onto that is very less. Now, let us look at so this was officially with the core of solid graphite, which was known then as black lead. Even today people call it lead pencil. Here is another type of pencil where a flat piece of graphite is kept in between 2 wooden pieces. So, anyway, the point here is it is a brittle material, and to be able to write you need some kind of stiffener around it. That is what the wooden pieces are for. Now, look at the rightmost picture, where you can see this pencil when you write. Okay. When you write, essentially what is happening is layers of graphite gets attached to the paper. Okay. Now, how that is possible? Because of this chemical structure of this graphite. You can see the yellow circles, or the picture on the right side of the screen, the chemical structure, which is this. Okay. Now, that you can see 3 layers on this drawing itself, right? Layer 1, layer 2 and layer 3. Okay. Now, these 3 layers just to demonstrate. Now, when you write with a pencil, so layer by layer gets attached to the paper or whichever surface you are writing. That is essentially what happens, and that is what makes it easy to write, or makes it a suitable material to write. Now, this why the layer by layer is getting detached from the graphite stick and getting attached to the paper, because the vertical lines here in this drawing, which are actually weak binding force or weak bonds as compared to the other bonds which are horizontal in nature in this drawing. Okay. So, these are all weak bonds. So, what happens as you apply the lateral force while writing, these bonds get broken, they get broken. Okay. So, if this layer is broken, then that means the lowermost layer, if this set of bonds are broken, the lowermost layer will get stick to the paper and so on. I think it is clear now. So, we have weak bonds and strong bonds. Now, look at the left side where you have a diamond example, where you have again very strong bonds. So, it is not very easy to write with a diamond, even though both of these are made out of carbon. So, the bonds play a significant role in whatever the material property we are talking about. Okay. Now, why in the case of diamond, though this carbon atom does not get detached, because all the bonds which you are seeing over there, they are all very strong bond, or they are all covalent bond and they are very strong. Whereas, in the case of graphite, the right side picture, they have both strong and weak bond. This is a strong bond and this is a weak bond. All the vertical lines are weak bonds. Now, that is the reason mainly why because of which we are able to write using a pencil. Okay. Now, some recap on some fundamental things about atoms, etc. We will just very quickly go through this. You already know this, I just wanted to refresh. Atom excuse me, consists of nucleus and electrons. You can see the nucleus here and then electrons around it. And what is a nucleus consists of both protons and neutrons. What is atomic number? It is basically the number of protons. Atomic mass, it is a mass of protons and neutrons. And then also the Avogadro number, which indicates the number of atoms present in 1 mole of the 1 mole of, if it is electrons, the same thing. Okay. Now, looking at atomic models, this is the left side image, shows kind of evolution of different models which describe atom, like starting from Dalton's model in 1803, then Thomson in 1904, then Rutherford in 1911, Niels Bohr in 1913, and finally, we have this Schrodinger's model 1926, in which you can see that in Niels Bohr model, you can see this well defined orbits are told, right. But later on, based on Schrodinger's model, it said it is not well defined orbit, but rather there are cloud of electrons. So, their electron could be anywhere in this region. Okay. Now, look at the picture on the right side, the same cloud it is redrawn, shown here. Okay. This is that cloud we are talking. Now, if you draw the vertical line here, that is the position of the nucleus. So, nucleus is here. Now, as you move away from the nucleus, okay, the distance from the nucleus, what is the possibility of finding a electron? So, that is what is drawn in this probability density function. Okay. Now, you can also imagine that as a cross section drawn like this. If this is the section, okay, if this is the section, let us say AA, and distance from the nucleus along the section AA is what is drawn. Okay. So, as you come to the center of this orbit or cloud region, you can find that is the probability where finding an electron is very, very high. Now, now we just talked about there are cloud and all that, then how it is actually organized, or how is the electrons configured in a particular atom. So, there are something called principal quantum number, where we talk about 1, 2, 3, 4, and then there is designation given to each of the shell, which are K, L, M and N, and then there are subshells which are S, P, D and F, S, P, or you can say S, P, D and F. Okay. So, in the first shell you have only S subshell, in the second shell you have S and P, in the third one you have S, P and D, and then in the N you have S, P, D and F. Now, number of states, you can see S1, S1, that is what it is, the number of states, and then you have number of electrons per subshell and per shell. So, this just to recap, we all studied in the previous, before coming to engineering colleges. So, this is just to recap it, so that I also wanted to emphasize that these are important to be remembered when we talk about materials. Now, most important thing in all this is the valency. What is that? It is the number of electrons that must be lost or gained by an atom to obtain a stable electron configuration. Okay. And now these depending on the number of valence electron, the type of bonds, the number of bonds that can be formed is also very much dependent on the number of valence electrons which you have. Now, in the previous slide I showed a table like this. The same thing you can look at here also in the sketch here. First is 1s and then 2s and then 3s and then 2p, 3s. I think I mistakenly told. First 1s. So, you just follow this line 1s, 2s and 2p, 3s and then 3p, 4s and then 3d, 4p, 5s, like this. You will start filling the electrons in around nucleus. So, that is how then when we look at electron configuration, this is how they are organized. Now, this is a different way of representing the same thing, and it is easy to look at individual electrons how it is. So, you can see first shell in S subshell. I am looking at this. Let us talk about an example of sodium atom, where you have first shell and S is the subshell. 2 electrons are taken there. Next 2 electron goes to 2s and next 6 electrons goes to 2p and then 1 is left. One more. Now, what will happen here? Instead of filling this, we don't, this is it, you have only 11 electrons available. Now, look at the picture on the right side or the sketch on the right side. You can see that there is this 1 plus or plus 1. What it means is this particular one is lost or given to another atom. For example, if you are talking about sodium chloride as a case, that 1 electron is given to the chloride. So, it goes out. Now, when it goes out, you have this 6 plus 2 is equal to 8. 2 plus 6 is equal to 8, and you have a perfect octet configuration by losing or giving away 1 electron. Whereas, in case of chloride, where you can see that 1 electron is taken from somewhere else, and hence you have a negative charge. So, 1 is taken and you have a negative charge. So, again this in this 3p you have 6 and then here you have 2. So, combining you get 8. Here also you have 8. So, this is how the octet configurations are formed, and then there are other 2 more examples, one on barium where you see this 2 plus. So, barium typically it gives away that 2s electrons or 2 electrons, and in case of oxygen typically it takes the 2 electron from some other atom and then you get this 2 minus as the charge. So, this is just the charge. All this you can see here, this is charge for sodium is plus 1, for chloride it is minus 1, barium 2 plus 2 and then minus 2. So, this is typically how these electrons are configured. Now let us get into a little bit on the interatomic forces and the distance between atoms, and how they behave when you apply a force in compression and in tension. So, that is what we are going to look at. So, it is a typical Condon-Morse diagram. I will show it in the next slide. So, you can see here this case is 2 atoms in equilibrium, or they are not necessarily touching each other, but they are at an optimal distance between them. So, the net the energy level is at the lowest energy level. So, the lowest energy level here. Now, when you compress these 2 atoms together, you are getting this state here. You compress. So, the distance between the atom is going to decrease, then definitely there is some repulsive forces created and then energy level is high. And when you pull them apart, which is this case here, there also the interatomic distance keep increasing when you pull atomic distance between the two atoms, and as you pull there is some kind of attractive forces generated, okay, which keeps the material together. So, this is why when you try to stretch something there is a reaction from the material which you experience. So, that is because of that attractive forces. Now, let us look at the same graph in a little bit more detail. So, now focus on the left side of the graph where you can see the interparticle or interatomic distance is the abscissa and lattice energy is the ordinate, okay, or the distance versus the energy level. Now, look at this, the top dashed curve which indicates repulsive force which is acting, and the bottom there is also a dash curve here, you can see here this goes like this, and that indicates attractive forces. Now, when you add these repulsive forces and attractive forces together, you get this solid curve like this one, you get this solid curve, okay. You get this solid curve by adding attractive and repulsive forces. Now, corresponding to this lowest energy level here, there is a R0 which is the interatomic distance at that level, okay. So, we are going to call it R0 and then U min, or that is the lowest energy level associated with those two atoms. Now, and assume now that this is a very high U min, the magnitude of that is very high, and that we can it indicates that it is a strongly bonded solids, or the bond is very strong. Now, compare this graph to the one on the right side. Now, you can see that if I draw this U min here, it comes somewhere here. In this case, the R0 is almost similar, and then but the U min has significantly reduced. That means low level of energy is required to break this bond, okay. So, U min in case 1 is more than the U min in case 2, the magnitude, okay. So, we can say that the case in 2 is actually a weakly bonded solid. The bond is very weak. It is easy to break that bond in the case 2 because the energy required to break is very low as compared to that in the first case, okay. Now, how to actually even look at to compute these forces, etc. We can look at the top graph. It is same as what I showed in the previous slide. You have U min, R0, and U is the graph and the ordinate and the abscissa R, okay. So, same graph like in the previous slide, but focus on this U min and R0, okay. So, this W0 it is actually U min, you can use this, I copied from the textbook. So, it came like that, it is okay. So, U min which now from this energy versus interatomic distance graph, can we actually get force? Yes, we can, and now that is basically the derivative of this du by dr with a negative sign here, okay. Now, slope of, so when you say this force, that is this curve on the bottom diagram, this is the curve we are talking about. Now, this curve here is repulsive force, this curve here is attractive force, okay. So, the summation of that is the curve which goes through the center of that or to the in between, that is this one, okay. Now, slope of this curve at this point, okay, that is at R0 is approximately linear and gives a measure of the restoring force or the reaction where that acts on the atom for small displacement. So, when you stretch a little bit, there will be a reaction to keep the materials together, and that is that force representing, and I will show more detail or more clearly this on the next slide. So, here you can see on the top right sketch very clearly the df by dr which we are talking. So, the slope of that in the red curve, which is a strongly bonded material, the slope is higher. That means when you try to pull, there will be a lot of force acting against the pulling force. The blue one is a weakly bonded thing. That means when you try to pull, the force generated is still going to be not that high as in case of the red one. So, you can see, look at the slope, let us say I am going to call it R, or let me call it strong material and weak material. Okay. So, the slope of that line at R0 is actually smaller in case of W material or the weak material as compared to that in the stronger material. Okay. So, the slope of this line and this line, two lines. Now, and also that is straight over there, that indicates we can actually determine the modulus of elasticity, that indicates that. If I take the from this, if I convert that into a stress and strain thing, then I can actually calculate the modulus of elasticity. So, this curve, if you look at it, it is also very similar to a stress strain behavior. Typical metal or any material, if you take the stress strain behavior, if I draw it here for strain and stress, you might expect some material having this kind of behavior. So, this is the region we are talking about, that linear region is this. Okay. So, this is that linear region we are talking. Okay. Now, tensile and so you have also non-linear region, that is like when you have more strain in the material, then it becomes non-linear in nature, that is this kind of region or this kind of region. Okay. So, when the stress or when the strain given or the when at the beginning of the stretching you have very low strain, and that point there will be a reaction from the material, and that kind of indicates the elastic modulus, and it is straight, the curve is straight line in that region, but as you keep pulling, the curve becomes non-linear. Now, tensile strength, when atoms are far apart, the material ruptures, or at a point where the reaction provided by the material is less than the action provided by the pulling force, or the attractive force is less than the pulling force, then the material start rupturing or it fails. And that is a point over here on the right end of this over here, this is that point. Now, when you talk about compressive strength, the possibility of pure compression failure is very limited. Why? Because as you keep pushing the material, the atoms together, there will be repulsive forces generated which will prevent it from getting too close. But what eventually will happen at that time is, typically there will be some lateral movement happening, instead of coming it will just try to slip and all that. So, that is, I mean, when you look at a concrete prism specimen also, you will see that when you compress it, it does not compress by reducing the volume of the material, but rather it undergoes the shear failure and all that, which because of the movement, horizontal movement. Anyway, so but yes, it looks very nice that we can get this Condon-Morse diagram at atomic level and then predict how the macro behavior, but it is not always possible that way. Why? Because when you talk about a single atom, it is not the same way it is going to behave in a group of in a macro scale, because there will be a lot of flaws or imperfections in the material system. Things in a atomic level is not same. When you put a lot of atoms or lot of molecules together, then there will be a lot of imperfections in the system or flaws in the fissures, cracks, etc. So many things will be there, which we are going to cover in next few lectures. But for now, you assume that there will be a lot of imperfections in the system, and because of these imperfections, the macro behavior may not exactly match with the micro behavior which is represented in the Condon-Morse diagram here. Okay. Now, let us look at how the shape of this diagram, or what does it mean when it or how it is related to the thermal expansion, coefficient of thermal expansion, or how we can use these graphs to understand the coefficient of thermal expansion. So, let us look at the case of a weakly bonded material on the left side. there I put high alpha, that means high coefficient of thermal expansion. That means this delta R is large for a similar change in temperature. Now understand this curve here. You can see this curve, it goes like this, the same curve which we were talking in the previous slide. Okay. Now look at T0, T1, T2 and T3. 4 different temperatures we are talking. Now at T0, this solid black curve is the curve. Okay. Now what about at T1? If I take this here, the curve might change. The curve might become something like this. At T2, that is here, the curve might become something like this. At T3, that is here, the curve might become something like this. So the curve keeps changing. Okay. Now this black line, here is the locus of all those bottommost points at different temperatures. Now what you want to know in this from this graph is that, let us say you look at this point and this point. Okay. So that we have R0 and R0 prime. R0 prime is for temperature T2 and R0 is for temperature T0. Now if we can get that delta R, okay, so that is, I put this dash line here so that it is not a fixed line. Okay. Here also same thing, its dash means it is varying, that is just to demonstrate that horizontal distance. Okay. Now this delta R, that means R0 prime minus R0, if it is more, okay, that means the material dimension has changed more as the temperature change from T0 to T2. Okay. Now look at the case 2, if I take T0 and T2 here, okay, so this if I draw here, now here in the case R0 prime will be somewhere like this. R0 prime will be somewhere like this. Now that delta R in second case, for the same difference of T0 and T2, it is much smaller than what is in the first case. So definitely we know that delta R in second case, which is a strong bond system, is smaller than delta R in the first case. Okay. So as you go from left to right, delta R increases, sorry, delta R decreases. Okay. That means the alpha also decreases, coefficient of thermal expansion also decreases. So in general we can say, if you have strong bond systems, then you can expect the material to have a low coefficient of thermal expansion. That means the deviation in the dimensions of the material might be very, very limited. And also another thing to look at is not only the width but also the depth. The energy required here also is very, very large in the case of strong bond. We already discussed this in the previous slide. But anyway, the point is depth and width of the well is this curve shape, indicates the size or magnitude of the coefficient of thermal expansion alpha. So why this is happening? As temperature increases, more vibrations occur, material starts to expand, more vibrations, so atoms tends to get separated. So eventually the material expands and then solid become liquid, liquid becomes gas, and then interatomic distance increases and eventually tensile strength also decreases. And you can think of many materials where at higher temperature the strength of the material is, or mechanical behavior is typically poor in nature. Now this is an example of what I just mentioned. This is from in literature. You can see here at different temperature, this is the 0 degrees and 50, 65, about 80 and 100. So how the curve is changing. In the previous slide it was like a textbook drawing, here it is a real example of something. So you can watch this in this link.